Okay, good morning all. Let's start with the today's lecture. Let me share the screen first. Okay, I hope the screen is visible. Okay, in today's lecture we'll be starting off with the module 5. Okay, and the first part of the module 5, that is, first of all, this module 5 is divided into three chapters, but we will discuss the initial part of the module 5, which will be there for your third eye. So this module 5, it consists of three basic uh, discussion topics. Let me make it full screen. Okay. Yeah. In this module 5, we'll be discussing the topics like evaluating the hypothesis, instance-based learning, and also we'll be looking forward for the reinforcement learning at the end of this module. Right. So the evaluating hypothesis part will be there for your third eye. So in this evaluating hypothesis, we'll be discussing about the motivation behind this evaluating hypothesis, why there is a need to evaluate the hypothesis, right? Then we are going to estimate the hypothesis accuracy. We'll be having a look upon some basics of sampling theory, basic fundamental principles there, right? Basic formulas for sampling theories as well, and then a general approach for driving confidence intervals. Right? We will discuss what is these confidence intervals as and when we proceed. Then we are going to discuss the difference in the error for, let's say, when we consider two hypotheses. What is the difference in the error that we get? We will be discussing that as well. And ultimately, by the end of this particular chapter, that is evaluating hypothesis, we'll be comparing the learning algorithms. Right. So motivation and estimating hypothesis accuracy is what we are going to see in today's lecture. Right. So starting off with the motivation, what is the motivation behind having this concept to evaluate the hypothesis? Why do we have to evaluate the hypothesis? Right. So as you see here that there are two different reasons why we have to evaluate the hypothesis. First one being the bias in the estimate, right? The bias in the estimate, by that I mean that let's say when we have the observed accuracy, right? Whatever the accuracy that we get, the observed accuracy of a particular learned hypothesis, right? How it will be learning the how it will have this observed accuracies when we put this hypothesis under some training, right? When we put this hypothesis under some training examples, and then we'll make the hypothesis learn. So whatever the accuracy that we get, that is our observed accuracy, right? So this observed accuracy of this learned hypothesis over the training example uh, is often a poor estimate, right? It can be a poor estimator. Why? Because it has estimated the accuracy depending upon the training examples. So we cannot guarantee that whether this accuracy will be remained, uh, for the further examples, the unobserved examples, right, or the examples which we are going to encounter uh, in the future. Right. So we cannot say that, I mean, this particular estimator can be a very optimal. This estimation can be very optimal given any training data set. Right? So this observed accuracy of this learned hypothesis over this training examples is often a poor estimator, we say, right? Poor estimator of its accuracy. Why poor estimator? Poor estimator of its accuracy over the unseen data of the future examples, the examples which we have not given as the input to the model. So that way we can have the bias in the estimate, right? So how to obtain this unbiased in the estimate? How can we get this unbiased estimation, right? So to obtain this unbiased estimate of whatever the future data that we are going to process, which is nothing but the future accuracy, right? To obtain this unbiased estimate for the future accuracy, we can test the hypothesis on some set of examples which are given as the test data, right? Instead of training data, we are going to test this uh, future accuracy of this particular estimation by typically testing the hypothesis on some set of test data instead of the training data. Now, this test examples, this test data, what we say here, training test examples, they are chosen independently of the prior training examples what we have seen, right? Prior training examples what will be given as the input to the hypothesis, right? So that's how we can have the unbiased estimation in the for those learned hypotheses, and then we can say that it is somewhat a good estimator than a poor estimator, right? Second aspect, the second reason behind evaluating the hypothesis, the need to evaluate the hypothesis is the variance in the estimate. Why variance? I would say is because even though when we have this so-called fairly good estimation for the testing examples that we are going to give for the hypothesis, right? Instead of the training data. So even though when we have this unbiased estimate for the future accuracy, the actual measure, the measure of the accuracy can still be varied, right? The measured accuracy can still vary from the true accuracy, whatever the estimated accuracy that we have computed, it can still vary from the true accuracy, we can say, right? Why? Because there can be a variance, there can be a difference, right? It depends upon the modification or the change or the any makeup of a particular set of tested examples. So if there is any change or any modification or any made up value or a make up the value for set of test examples, then we can say that there can be a variance or the measured accuracy can still vary from the true accuracy, right? And another aspect to it is the smaller set of test examples that we have. This we have already seen that the smaller set of test examples that we have, the greater is the expected variance, right? So the smaller set of test examples that we are processing, there is high chance that we can have a greater variance, right? So the more the set of training examples, lesser can be the variance, right? So these two important reasons is what we have as the motivation behind evaluating the hypothesis. These are the reasons which help us to decide to evaluate the hypothesis. So first one being, of course, the bias in the estimate. Second is the variance in the estimate. So what are that we are looking forward here, right? We are interested in these two questions. We need to answer these two questions here, right? What are these two questions that we are interested in? The first one being the, let's say when we have a given hypothesis H and a data sample containing n examples, right, drawn at random according to the distribution D. Please note the notations here. These notations are very important, right? Let me repeat that. Given a hypothesis H and a data sample containing n examples drawn at random according to the distribution D, what the question is that what is the best estimate of the accuracy of hypothesis H over future instances drawn from the same distribution, right? So hope the question is clear, right? For example, let's say, let me repeat it again, that uh, let's say we have a given set of hypothesis H and few data sample, let's say any number, n examples, 10, 15, 20, any set of examples that you consider, right? Given a hypothesis H for the sample data with n examples which are drawn at random according to some distribution D, okay? So this is the distribution D. The question is that what is the best estimate of the accuracy of that hypothesis over the future instances drawn from the same distribution. Right? This is the question that we need to address here. Right? What can be the best estimate? How to compute this best estimate? Right? The second question is that what is the probable error in this accuracy estimate? Right? Is there any error? First of all, is there any error? If there is an error, what is the probable error in this accuracy estimate is what we are going to address here. Right. So in the further slides, we are going to answer these two questions. Right. That how do we compute the best estimate for the given accuracy of hypothesis H, right? And what is the probable error for the accuracy estimated, right? So, discussing the first thing, that is estimating the hypothesis accuracy. In this, we are going to discuss some important aspect like sample error. What do we understand by a sample error? What is a true error? What is a sample error? Right? And then we are going to discuss about the confidence intervals for the observed hypothesis error. Right? Whatever the observed error that we have encountered for particular hypothesis, what is the confidence intervals for those observed hypothesis errors, right? How do we compute the estimators? What do we mean by estimators, and how do we compute uh, estimators, right? How do we end up having evaluating the hypothesis? Then we are going to also discuss about the binomial distribution, normal distribution, and the central limit theorem. Then we are going to discuss about the paired uh, tests, right? Paired t-tests, and then ultimately comparing the learning methods, right? So let us start off first with understanding what do we mean by sample error and a true error, right? As the name suggests, sample error and a true error. So sample error is something that we have got as an example, as a sample, a specimen, right? A sample error, which is not the actual error, right? And as the name suggests, the true error is something which is existing, which is real time. The error is actual, right? So sample error of a hypothesis with respect to some sample S of instances drawn from the set of instances capital X is the fraction of S, right? It is nothing but it is the fraction of the sample S that is misclassified, right? So this can be termed as a sample error. So the error which has been basically misclassified from the set of the sample instances capital S, right? So how do we define it? How do we put up in the formula, right? The sample error basically here is how we are going to denote the sample error in the formula. So henceforth we are going to use the this particular denotion for denoting the sample error, right? So error S of H, it is nothing but the sample error for that particular hypothesis H, right? So the sample error of hypothesis H with respect to the target function F and the data sample S can be denoted as this formula, right? So as you can see, it is the summation of the dou function of the target function uh, f of x and the hypothesis h of x, right? For all the sample space S, but it will be totally divided by the number of training examples, which is n, right? Please don't forget this n here, which is nothing but the number of training examples for that particular set of samples, right? So where here, yeah, let me here that n is the number of examples in S, and the quantity dou of f of x comma h of x is 1 if the f of x is not equal to h of x, and if it is equal to if the f of x is equal to h of x, then it will be 0 otherwise. Right, so this formula is very important. This is what is the basic formula, the fundamental formula to define an error here with respect to the sample, right? So the true error, what do we understand by the true error? As the name suggests, it is the true error. That means that it is the actual error present in the set of sample data, right? So again, it is a misclassification, of course, but it is the error which is existing in the data, in the sample data, actually, right? So the true error of a hypothesis is the probability that it will misclassify, right? Please let me repeat the statement. Please pay attention here that the true error of the hypothesis is the probability that it will misclassify a single randomly drawn instance from the distribution D. Right? So this term is very important, that it will misclassify. Right? So that is actually a true error. There is an actual error there. So how do we denote it? Right? How do we define it properly and how do we denote it? The true error, as denoted as error d of h of a hypothesis h with respect to the target function f and distribution d, is the probability that the hypothesis h will misclassify. Right? That particular hypothesis h will misclassify an instance drawn at random according to the distribution d. Right? So how do we define it? So this is the formula for that. That is, error d of h is given as the probability of all the instances x belonging to the distribution d, wherein f of x is not equal to h of x. Right? So this particular symbol, this notation here denotes the probability is taken over the instance distribution d. Right. So this is the definition of our true error. Now, I hope the difference is clear between the sample error and the true error. So this is very important because this is the fundamental, two fundamental errors that we are frequently going to encounter here in this model. And depending on the understanding of this sample error and true error, we are going to set up a few more definitions like confidence intervals and those things. Right. So now the question arises, after having been discussed about this sample error and the true error. The question that arises is how good an estimate of this error D is provided by the error S, right? So in other terms, in simple terms, if I have to define it, the question again, how good an estimate of true error is provided by the sample error, right? So is the sample error that we have computed is helpful enough to estimate our true error, right? Is the sample error that we have computed is providing any insights? Is it helpful to estimate our true error, right? Because true error is something that we are more interested in. We are trying to reduce this true error as much as possible. Right? For that, we need to have a good sample error, fairly good sample error. We cannot have a poor sample error defining a good estimate for the true error. Right? So we need to have a good sample error which can provide us some help, some understanding, some insights to estimate better true error. So the better the true error that we have, the better the chances to have the accuracy, greater accuracy, right? So lesser the value of the true error, the better will be our accuracy. So it is important to have good estimate of the true error, and which we can get it from the sample error, right? But the question is how? How good an estimate of true error is provided by the sample error? So this particular question can be answered with the help of the confidence intervals for the discrete valued hypothesis, right? Now, what do we mean by these terms, right? What is the confidence interval, and what do we mean by the discrete valued hypothesis, right? So, discrete valued hypothesis, as we have seen already in the maybe I think in the model 2, right? So, we'll be focusing upon how do we estimate the true error provided by the sample error, right, using these confidence intervals. Right. So for that, in order to understand that, let us understand first that suppose we wish to estimate the true error. Right. Suppose we want to estimate the true error for some discrete valued hypothesis h. Right. So this estimation of the true error for this discrete valued hypothesis h is based on its observed sample error. right? Whatever the sample error that we have computed, or whatever the sample error that we have observed, right? Which is nothing but error S of H. That is our sample error. So the estimate of the true error will be depending or based upon the observed sample error over some sample space S, right? Over some sample space S. Now, the condition here is that where the sample space S contains n examples drawn independent of one another, right? Of course, and independent of the hypothesis H as well, right? But according to the probability distribution T. Right? So this is one condition that we have, that the sample space contains n set of examples drawn independent of one another and the independent of the hypothesis H according to the probability distribution D. Right? So this is the one condition that we have. Another is that, let's say, suppose that n is greater than or equal to 30. This is just for an example. Let's say that the set of training examples, number of training examples n, is greater than or equal to number of, let's say, a number 30. Right? The third thing that to be focused here is that hypothesis H commits the R errors, commits the R errors over the n examples, right? So the hypothesis H commits R errors over these n examples, which can be denoted using this particular formula here, right? That is, error S of H is equal to the ratio of the R errors, right, divided by the number of training examples. Right. So we will see what are these errors and how do we compute it. But under these set of conditions, like these are the different conditions that we have. Right. So under these uh, conditions, there is some theory that we are going to put up here. Right. So these are the statistical theory, right? These are the statistical theory which allows us to make some assertions, right? Now, what are these assertions? The number one assertion is that, let's say, we have a given number of other information. We have given no other information. Pardon me, that we have not given any other information, that the most probable value of the true error, that is error d of h, is the sample error itself, right? We have not given any other specific information, but just that the most probable value, right? The most probable value for the true error is the sample error itself. That is the most probable value that we can have, right? This is the first assertion here, right? Another assertion with respect to the statistical theory here is that with approximately 95% probability, right? Approximately 95% probability, the true error d of h, lies in the interval this. Right? So approximately 95% of the probability that the true error will lie in this interval. That is the sample space error, the sample error, sorry, that is error s of h plus minus 1.96 root to the ratio of this sample error, the difference of the sample error from 1 divided by the number of training examples. Right, so this is the standard formula here, that is for, if we have to say that approximately 95% probability, that is the true error, lies in this particular interval. There's one more thing to be understood here, that however we do not accept this to be perfect estimate of the true error, right? This cannot be the perfect estimation. There can be still some chances that there can be a better estimation. We cannot say that this can be the optimal estimation, right? Because these are we are a very hypothetical situation, very hypothetical data, some statistics that we are considering here, right, for given values. Right. So with this, let me show you a table here. So this particular table, as you can see, we have two parameters here. That is the confidence level. Let's name it n percentage. N is the any number of the confidence level, right? And the constant z for that particular level n, right? So the constant zn and the confidence level n percentage is what you see here in the table. So these values of this is the table wherein this constant the value of this constant Zn for two-sided n percentage. It, it is for the two-sided n percentage confidence intervals. So for example, let's say for confidence level 50%, we have some constant 0.67, right? And so on for the constant 1, we have some confidence level 68, and as and when we proceed, that 1.28 confidence goes high, confidence level goes high 80%, 1.64 90%, 1.96 95, 2.33 98, and 2.58 you can see it's the maximum, that is 99% confidence level. Right, so these are the confidence intervals, the range that we have for different values of constant Zn. Okay, so this using this is what we can. This can form the basic understanding of evaluating the hypothesis. Now, once we understand these things, we can successfully be able to estimate the hypothesis accurately. Right? So when we have the understanding of this, that what is the bias in the estimate? Let me show you back to the slide. When we understand that what is the bias in the estimate that we are doing, first of all, what is the variance in the estimate? This will show you what is the need of evaluating the hypothesis, right? And once we evaluate it, there are a few questions that we'll be addressing here. Uh, in order to answer those questions, we need to understand this concept of, what do we mean by this sample error, what do we mean by true error, and these uh, definitions, these concepts is what will be helpful for us to evaluate and estimate the hypothesis more accurately, right? So that is the need of estimating the hypothesis accuracy, right? So with this, we shall conclude the today's lecture, and further more as and when we dive into it, we will look forward that how these sample errors and true errors are important to find these confidence intervals, yeah, right? And then how can we form a basic sampling theory, right? How can we have basic definitions and some statistical facts to understand what are the different types of terminologies which will be helpful enough to estimate the hypothesis more accurately, right? So there are different aspects like error estimation and estimation binomial proportions and those things which will be taking forward uh, in as and when we discuss some basic fundamentals there in the sampling theory, right? Like binomial distribution, then we have some random variables, expected value, right? Normal distribution, binomial distribution, then central limit theorem, and so on. Let me show you that slide. Yeah. So binomial distribution, normal distribution, and central limit theorem, and ultimately we are going to see how can we compare those learning methods. Right. So that's all for today's lecture. If you have any doubt, you are free to ask. Anybody having any doubt? So if you have any doubt, you can ask me anytime. But make sure that you revisit these slides when they are uploaded on the YouTube, and then make your own notes and understand it related to some examples. Of course, we are going to see further examples as and when we proceed, but try to relate it to your examples as you are already working out with your final year projects, and there's a high probability that you guys have been working something similar to evaluating this hypothesis, right? So that will be very helpful for you if you relate to a real time example and analyze, like visualize these concepts being uh, applied there, and then what result that you get, right? So when you try to relate to some examples, you try to connect better, and we'll have a better picture of how exactly these things are getting implemented, right? So instead of understanding it only from the theoretical point of view, always have a practical approach, a practical angle, which will help you understand these concepts more better, right? So with this, we shall conclude today's lecture, and we shall proceed further to your eyes. So, all the best for your eyes. Okay, thank you. You are free to leave the meeting.